Hello, everybody. Tonight we're going to take a look at inertia versus gravity. First thing we want to take a look at is how do they interact? How does inertia and gravity interact with each other, especially when we're dropping objects? Now, we're going to do a lab tomorrow that's going to consist of you testing out the theories that we're working on tonight. So let's start off with some background on both inertia and gravity. First of all, we have primary and secondary forces in the universe. Okay, now gravity is a primary force. Okay, along with electromagnetism, a weak force and a strong force. The secondary forces are buoyancy, pressure, mechanical, and obstructive. Inertia falls into this category. Now, let's take a look at them individually, and we'll see how things work out. Gravity is a primary force in our universe, and it has an acceleration of 9.81 meters per second squared. When gravity actually acts on a mass, it gives that mass weight. And these are critical things because this is what throws most people off when you're taking a look at trying to determine the questions we're going to ask today about the speed of objects and how fast they fall. So just don't forget about that. Okay, now we're going to move on to inertia. Now inertia is Newton's first law. Okay, and he actually came up with this law based on Galileo's experiments. Galileo came up with the experiments, but he didn't know how to explain them. He knew what happened. He knew that if you drop two objects of different weight or density, they would land at the same time. You know, everything else being equal, they land on the ground at the same time. And he did this off the Leaning Tower of Pisa. So I don't know if you remember ever seen any pictures, but that's that big tower that's leaning on the edge. We used to go up there and throw things off. So anyway, that's where Newton took it a little further and actually did some math behind it, and that's how we came up with this. So inertia is resistance of an object to change its state. So in other words, if an object is at rest, it tends to stay at rest. So it's going to take, and if it's in motion, it tends to stay in motion. Which means if an object is at rest, it has no acceleration. Right? Not moving, it has no acceleration. Acceleration is a change in velocity. Okay, so you don't have any change there, so it's going to be the same. And also, if it's moving at a constant velocity, there is no change in velocity. It's staying at the same speed. So again, it has no acceleration. Okay, that's going to come into play when we go to take a look at this experiment. Okay, now let's get some questions going. We have an anvil here, and we have a feather. Okay, which one's going to fall? Which one's going to hit the ground quicker? Are they going to hit at the same time? Okay, that's question number one. And question number two: does the heavier object have more force when it's dropped? So does this anvil have a greater force when it's dropped than the feather? Okay. Now we know that gravity times mass equals weight. So this is going to have a greater weight when it hits the ground. So it's going to have a greater force than the feather. We know that already. We've learned that before. Okay? And also, what part of the objects does the gravity accelerate? And this is where it gets interesting, and this is where it's counterintuitive. So this is something you're going to have to follow this very closely. I'm going to talk about it. I'm going to repeat myself a couple times, but it's very important. Okay, now, gravity works on a subatomic level. Okay, so in this object right here, in an anvil, we have protons, neutrons, electrons, and we got quarks, bosons. We got all kinds of neat little things in here. And the feather, we have the same things. We have neutrons, electrons, but they're not as densely populated. So this is heavy densely populated. This isn't. Okay, so there's your difference in the mass. Now, because gravity works on a subatomic level, it acts upon the smallest particles, which is like a quark. Okay, so what it does is, when it's acting on it, it acts on a quark the same here as it does here. But it does it individually, and it does it equally. So across all these particles that are here, it doesn't matter how many billions of particles you got in here, and say you only got 1 million over here. Gravity's still acting on one quark at a time equally. And that's why this comes down at the same time. It's not doing it as a total, it's doing it as an individual. Okay, let me go over that again. Gravity works at a subatomic level. Okay, it's not working on the anvil as it is here. It's working on the individual tiny little specks of particles in there called quarks and neutrons, electrons, and protons. That's what it's pushing down on. Okay, but it's pushing down on them equally and individually. Okay, here's an example. This will kind of give you an idea. If you jumped off a high dive of a pool and you had a ball in your hand, if you let go of the ball, is it going to go up in the air or is it going to come down with you? It's going to come down with you. So it doesn't matter. If this anvil was tied to the feather, they would come down together. But if they're separate, it's the same thing. So that's how you have to try to take a look at it. And tomorrow you're going to have a lab to prove this. So you're going to actually, in the lab, we're going to have, in class tomorrow, we're going to work on this lab activity, and you're going to actually do this. You're going to do this a couple of different times in a couple of different ways just to make sure that you understand this principle. This is a very important principle. Okay? So what I want you guys to do, I do have a little video for you to watch after this. I'll give you the URL on it. It's a Roadrunner cartoon. It's actually pretty funny. I used to watch it when I was a little kid. And basically it's about a coyote trying to catch a roadrunner. And the roadrunner keeps trying to use physics to try to catch him and always fails. And some of his physics don't work. It doesn't make any sense at all. And what I want you to do is, as you go through the cartoon, I want you to pick out a couple of ones that completely go against the laws of physics. And I want you to bring them up in class. I want you to write them down. And in class, we're going to bring a couple up and we're going to talk about them. So I want you guys have a good night. Watch that video. And tomorrow we're going to practice this lab.